All right, let's share the screen. And all right, so today we're going to start going over chapter 2, which is all about the chemistry you need to know to understand microbiology. Okay, and so that's chapter 2, biochemistry basics. And today we're going to be covering atoms, bonds, and water. Okay. All right. Here is an overview of what we're going to be covering. So we'll go over this week's learning objectives. I'll open it up to questions. We'll talk about atoms and bonds, characteristics of water, chemical reactions, and what to do for next time. Okay, so this week will provide you a foundation to be able to meet the following learning objectives. Identify microbial structures and connect the structures to their functions. Identify necessary components and processes in microbial metabolic pathways. Identify key agents and processes of microbial information transfer. And identify key agents and processes. Oh, I've got that twice. You only have to learn it once. Okay. All right, any questions? Okay, if you think of some, let me know. I'm happy to stop and answer any questions. Okay. Let us go ahead and move on to the first topic. First off, while I'm getting the whiteboard set up here, chemistry can be hard. It can be hard. It's dealing with things that are too small to be seen. And a lot of what goes on the atomic level is not what we normally see with our eyes. Okay, things are different when you get really small. Okay, so I will be using some what I call macroscopic examples. Okay, things that we can see to try to explain and help you understand what's going on the very small atomic level. Okay, sometimes the analogies kind of break down, but you know, they're a starting place. They're a good way to start to understand this topic. Okay. All right. So first off, atoms are the smallest unit of matter that still behaves like when there's a whole bunch of them. Okay. So what do I mean by that? If I take an atom of oxygen, it's still going to behave like oxygen, like a full canister of oxygen that I would use if I were a respiratory patient. Okay. Same thing with, you know, atoms of hydrogen, okay, gold, silver. When you break them down to the atomic level, they're still going to behave the same way. Now, you can break an atom down further than that, but then it stops behaving like the element that we're familiar with. Okay. Okay, so here's the official disclaimer. I'm going to be using the Bohr model of the atom to explain how things behave. There's a more later, more accurate model that we use, but this is a good way to start out. So later on, when you take another chemistry class, you'll cover the Bohr model and then you'll move on from there. Okay. All right. So let's start out with the simplest atom, the simplest element, hydrogen. Okay. All right. So a hydrogen atom kind of looks like a planet with an orbiting moon. Okay. So we have at the center, we have a little particle that has a positive charge. Okay. So if you're talking magnets, or if you're talking like a battery, where you've got a positive terminal and the negative terminal, this is the positive side. Okay. And we call that a proton. Okay, you've probably heard of a proton before. Okay, so hydrogen is very simple. It only has one proton. Now, zipping around the outside like a little moon, we have another particle that has a negative charge that is called an electron. And the positive and negative charges are attracted to each other. Okay, so the electron goes zipping around the proton in what we call a shell or an orbital. Okay, reflecting the Bohr model of, it looks like a little moon orbiting in an orbital, a planet. Okay, and that's a hydrogen atom. Okay, so that is the most simple atom. Okay. Now with bigger atoms, okay, we've got more protons. Okay. Oh, by the way, we abbreviate hydrogen as H. Okay. So let's go ahead and go with oxygen. Okay. And I'm not going to draw all of the oxygen protons because there are 8 of them, but we'll do a representative sampling. We'll do 4. And then later on, I'll draw some half circles to kind of show. Okay, so these positive charges repel each other. Okay, they don't want to stay next to each other. Kind of like if you have 2 magnets, and if you try to put the 2 positive ends together, they push apart. But if you flip them around, then the negative will be attracted to the positive. Okay, so to help these guys stay together, we have another particle. Okay, in addition to the proton, we have what are called neutrons. Okay, and they don't have a charge, so they kind of hang out in between the protons and act as a buffer. Okay, so there are an equal number of neutrons as protons. Okay, and we'll indicate that there are 8 there. And we'll go ahead and put the rest of our protons in there. We'll put 1 in here. Okay. All right. So oxygen has 8 protons, and it has 8 electrons. Okay, and once again, the electrons are going to orbit this center, okay, which we call whether it's 1 proton or several protons and neutrons together, we call this a nucleus. Nucleus. Okay. All right, so the electrons, okay, we have room right close to the nucleus for 2 electrons. Okay, and we call that the first shell or the first orbital, and there's room for 2. Okay, in the next couple of orbitals, which is as far as we're going to go in this class, okay, we have room for 8. Okay, so I've got 8 protons, I've got 2 electrons in the first shell, so that means I have 6 electrons in the next orbital or shell. I'm going to put these guys here. Okay, so it's kind of like the moons of Jupiter. Okay, I've got some orbiting closer to Jupiter. I have some that are orbiting further out. And normally they don't go in like that, but you know, my drawing skills are limited. Okay, so now I'm going to give the atoms human emotions that they don't really have. Okay, so hydrogen would really be happy to pick up another electron. Okay, and then it would have a full shell. Oxygen would really like to pick up 2 more electrons. Okay, then it would have a full outer shell. Okay, we call these outer shells, the valence shells. Okay, valence electron shells. Okay. All right. So how do they get these other electrons? Okay. If we are talking to hydrogens, okay, and hydrogen in the atmosphere exist as pairs. And what happens is this hydrogen atom, okay, and this hydrogen atom say, hey, how about if we share? Okay, let's share these electrons. So this electron will spend some time over here. This electron will spend time over here. So between them, they share both of their electrons. Okay, because they're sharing, we call that a covalent bond. Okay, and we spell it CO lowercase v ALNCE. Okay, but I split it up so you can see where we get the words from. Okay? Oxygen does the same thing, and we represent this sharing by showing a line. Okay, so oxygen will get together with another oxygen in the atmosphere, but instead of sharing one electron between them, okay, so like this one, this electron spending some time around both of them, this one spending time around both of them. So this line refers to a pair of electrons that are being shared. Oxygen will share 4 electrons, 2 pair between 2 oxygen atoms. Okay. And because these atoms are the same size, the electrons spend equal amounts of time around each nucleus. Okay, so we call that a non-polar. Oops, keep moving my screen when I want to write. Okay. All right, how are we doing so far? We're doing all right. Okay, just for the sake of room, I'm going to get rid of my drawings. Okay, and for this next part, I'm going to draw just the, for the nucleus, I'm going to draw just the abbreviation of the element name. Okay, but I am going to draw the electrons in the valence electron shell. Okay, so let's go ahead and get the 6 electrons in the valence electron shell of oxygen up here. Okay. So in the atmosphere, like I said, hydrogen is in pairs, oxygen is in pairs. But if I take hydrogen in an oxygen-rich atmosphere, like what I'm breathing right now, say I've got hydrogen in a balloon, okay, or in a blimp, okay, like the Hindenburg, and I add fire, okay, what's going to happen is we're going to break the bonds between this and between the oxygen pairs, and these guys are going to be able to get together. Okay, so hydrogen wants one, oxygen wants 2. So these guys can each donate an electron, and oxygen can donate an electron. Okay, and what will happen is these electrons will go zip, okay, zip, okay. But oxygen is a whole lot bigger than hydrogen, okay? So the electrons are going to spend more time around the oxygen with only occasional trips out here to the hydrogens, okay? Because it's bigger and it's more attractive. Okay? So what that is going to do is that's going to give the oxygen a little bit of a negative charge, okay? Because maybe instead of having 8 electrons buzzing around it, maybe it's got 9, okay? And then over here, sometimes this is just a lonely proton with the electron off visiting the oxygen, okay? They come back eventually because they are sharing. But hydrogen is going to get a slight positive charge. And I use this lowercase delta, which is kind of a funky Greek letter, okay, to show that it's a partial charge, okay? So what is H2O? If I were to draw this, I can draw this, whoops, 2 different ways. It helps if I put the right letters. What is H2O? Here's another way to write it.
Water.
Water. Yes. Okay. And water, the water atoms have this a little bit of charge. So I'm going to draw this over here just so you can see how it looks drawn a little different way. Okay. And so it's like a pole of a magnet. It's got a positive end, it's got a negative end, or like a battery. Okay. So if we're talking oxygen in the air versus water, is there a difference?
Repeat that.
Yeah, is there a difference between water? Okay, say at room temperature most of the time. Is there a difference between how we see water versus oxygen in the air? How would we describe water? Let's tell you what, let's go ahead and set up a fish tank, because I'm going to use the fish tank analogy later. So let's say I've got a fish tank. How would I describe the water versus the oxygen that's coming up from the bubbler? Okay, so we'll say that I've got a cute little clamshell here that opens and closes and releases oxygen. Okay, and we'll go ahead and we'll put a fish in here. We'll make it a happy fish. Okay, that is the wrong spot for the fish's mouth. There we go. And we'll put another one over here. How would you describe the water versus the air, or the oxygen?
I would describe it as you could physically see the water.
You can.
The air, the oxygen in the air, you can't see, but you could feel it and breathe it in.
That's right. Okay, so you can see it. Whereas oxygen, okay, is invisible. But you can feel it. Okay. What's another term that we would use for water when it's in my fish tank?
Is it because one is a liquid and one is a gas?
Very good. In this case, we've got a liquid and we have a gas. Okay, very good. Okay, hydrogen is also a gas. If we get it cold enough that oxygen becomes a liquid, it's really, really cold. Whereas water can be a liquid at, quite warm temperatures. Okay. Now, the question is why? Okay. All right, I'm going to get rid of my big water here. And I'm going to show you why water is a liquid at room temperature. Okay. In fact, it's a liquid until it gets really, really hot. Okay. And why oxygen remains a gas. Okay. So it's all because of this polar characteristics of water. Okay, so I've got a little bit of a positive charge here, a little bit of a positive charge here, because the electrons are spending more time around the oxygen. okay? When I get water together, water forms kind of like a cage because this negative charge is going to be attracted to this positive charge, okay? Kind of like static electricity. Yep. Okay, so remember, this is a covalent bond. We're sharing electrons, okay? Whereas this static electricity between the water molecules, okay, is a temporary thing, okay? But we call these hydrogen bonds. Okay, and they form anytime we have oxygen bonded to hydrogen, okay? Because remember, the oxygen is bigger, so the electrons that they share stay closer to the oxygen, okay? They're around the oxygen more than the hydrogen, or nitrogen bonded to hydrogen, okay? Because nitrogen is just a little bit smaller than oxygen, so it does the same thing, okay? So hydrogen bonds are these bonds between the slight positive and slight negative attraction between molecules, okay? Whereas the shared electrons between the oxygen and the hydrogen are a polar covalent bond, okay? Because they're actually sharing electrons. Now, here is a macroscopic analogy, okay? So it's kind of like the oxygen molecules are a couple, except for, of course, we have three, so it's a polygamous couple. This is where the analogy breaks down. But they can go to a dance and they can do a square dance and they can grab hands with their partners and swing from one to the other, okay? But the married couple are still a married couple, okay? Even though they're holding hands briefly with other dancers. Okay, does that kind of make sense? So hydrogen bonds are other people in the dance. Covalent bonds are you're married and you're sharing resources. You're legally sharing those electrons. Okay.
So they're basically swingers.
Sorry, what?
So they're basically swingers.
They're basically swingers, yes.
Okay.
But they're temporary attractions. So it's not like they actually go home together. It's just they're dancing with people that they're not married to. Like I said, this is where the analogy kind of breaks down. Okay, so those hydrogen bonds hold the oxygen or the water molecules together closer than they would be if they didn't have those hydrogen bonds. Okay. Now let's take a look at what happens with the oxygen over here. Whoops. Okay. So let's go ahead and put straight oxygen that's been bubbling up. So I've got oxygen here, and this bond is still a covalent bond, but it is a non-polar covalent bond. Okay, so there's no charge. So this oxygen is kind of like the folks who don't know the steps to the square dance, and they're sitting off to the side watching. They're not a part of the dance because they can't hydrogen bond. Okay. So water, when it forms this cage, okay, so I've got an oxygen here, okay, and here, and it's hydrogen bonding here, and this is hydrogen bonding here. The oxygen, which is non-polar, gets excluded, okay? And so the oxygen tends to, whoops, I did not change colors. Let's change colors. Oh, well, I'll make that another water. Okay, so these guys are hydrogen bonding with each other. the oxygen tends to stay with the oxygen, okay? And because we're forming this net, this cage, the oxygen eventually gets forced up to the surface. So if you keep fish, you know you've got to keep that aerator going because otherwise the water gets stagnant, okay? The oxygen leaves because the water has excluded it, okay? And then our poor little fish either die or they are the type like goldfish that can go up and gulp air, okay? Okay, now let's say this is a salt water tank, okay? And I put salt in. Oh, let's make salt purple, okay? So I drop salt in. What's going to happen to that salt? Yes, Courtney.
So the non-polar covalent or bonds have a neutral charge, you said, right?
Yes,
Okay.
they are
Okay.
neutral. They're neither positive or negative.
Okay. Okay. Thank you.
Okay, so I drop this, and this is a saltwater aquarium. Okay, so I drop salt in. What's going to happen to the salt?
It dissolves.
It dissolves, yes. Eventually, that clump of salt is going to disappear. But when I test the water, I'm going to find that there is salt all the way through, okay? Does the salt rise to the surface? No. As the water evaporates, because, you know, water does leave and become gaseous, especially if it's hot, okay? Then, you know, the concentration of water is going to drop and eventually my salt is going to crystallize, okay? But no, it's going to stay dissolved. Okay, whereas oxygen does not. Oxygen, I have to keep adding it to keep it in the water, okay? Or if we're talking, say, oceans or rivers or streams, the waves, you know, streams going over rocks, over waterfalls, that continually adds oxygen, okay? There's more oxygen in running water than in still water, okay? So what happens when I drop salt in? Okay, salt is a little bit different, okay? So let's go ahead and draw salt over here. I'm not going to do the whole nucleus with the electrons this time, okay? But salt is sodium chloride, okay? You may remember that, okay? NaCl. So in sodium's valence electron shell, it has one electron. Okay? It has a whole bunch in between there. But in its outermost shell, it has just one. Okay. And chlorine over here has 7. Okay. So to fill up its shell, chlorine needs just 1. Sodium, to fill its outer valence shell, needs 7. Okay. Now, sodium knows it's never going to get 7. It's just not going to happen. Okay. So what sodium says to chlorine is, hey, this electron is more trouble than it's worth. Take it, it's yours. You don't even need to pay me back. Okay. So this electron goes over to chlorine. Okay. And so chlorine now has 1 more electron than it has protons. So it gets a full negative charge. Okay. None of this funky delta partial charge thing. Okay. And sodium, because it has 1 fewer electrons than it needs, okay, or 1 fewer electrons than protons, it gets a full positive charge. Okay. And like the water molecules, hydrogen bonding, these guys are attracted to each other. Okay. So the positive charge, excuse me, there we go. Okay, the positive charge of the sodium is going to be attracted to the negative charge of the calcium, and those two are going to stick together when it's my cube. But once they drop down in, okay, the sodium can say, hey, how you doing, oxygen? Okay. And the chlorine can say, hi, hydrogen, how are you doing? Okay. Because this slight positive charge is going to be attractive to the chlorine. Okay. This slight negative charge is going to be attractive to the sodium. Okay. And that's why salt dissolves. Okay. Because it has a charge. And it can interact, it can be a part of the square dance. Okay. Whereas anything that's nonpolar that doesn't have a charge cannot interact. Okay. And so they sit around the outside and or they get shoved to the surface. Okay. How are we doing so far? Have I flipped your brains inside out yet? A little bit. Welcome to chemistry. Okay, so let's do a quick review. Okay, nonpolar. That helps if I spell it right. Okay, nonpolar covalent. Okay, is equal sharing of electrons. Okay. Polar covalent is unequal sharing. Okay. And we end up with a partial charge. Okay. This interaction that we see with sodium and chloride, okay, is called, it depends upon who you talk to, ionic attractions. And all of a sudden I forgot how to spell attraction, sorry. Okay, or sometimes you'll see it called an ionic bond. Okay. Technically, it's not a bond, it's an attraction, but you know, if you see it referred to as a bond, that's fine. Okay. This is where, let's see, I've got to move things here. Okay, ionic attractions are where electrons are donated or received. Okay, so chlorine received an electron, sodium donated it, okay, and there is a full charge. Okay. Now we have terms that we use, okay, to describe the relationship of these bonds, these attractions with water. Okay. So polar covalent and ionic attractions are what we call hydrophilic. Okay, they are water loving. Hydro for water, philic for love. Okay, Philadelphia is the city of brotherly love. Okay, that's where the Philly comes from. Okay, and they're going, yeah, since when? Yeah, that's what the name means. They had high hopes. Polar covalent bonds are also hydrophilic. Okay, so they're water loving. It means they'll dissolve in water. Okay, non-polar covalent. Okay, we call that hydrophobic. Okay, or water fearing. Okay, means it won't dissolve. Okay, how are we doing? Won't dissolve or it won't dissolve well. Okay. All right, so I'm going to get rid of some of these guys because I've got one more bond I want to tell you about. Whoops, I just got rid of all of them. There we go. Let's get rid of just these guys. We'll get rid of our sodium and chloride here. Okay. there are some molecules that have two characteristics, okay? So there are some oils, okay, lipids, we call them, okay, that they have a whole lot of covalent, non-polar covalent bonds between their atoms, okay? And so this part is hydrophobic, okay? Whereas on the other side, it has a bunch of polar bonds, okay? So that we've got a bit of a charge, okay? In this example, it's negative. So it would have a hydrophilic end, okay? So for this type of molecule, because it's got a part that's hydrophilic and we have a part that's hydrophobic, we call this amphipathic. Okay, so it's from the same root word as ambidextrous. Okay, ambidextrous I can write or eat with both hands equally well. Okay, amphipathic. Okay, it can be either hydrophilic or hydrophobic. Okay, all right, how are we doing? So this part would be able to join the square dance, and the hydrophobic part is gonna bring other hydrophobic molecules with it because they're gonna all cluster together, okay, outside of the dance. That's gonna be important when we talk about cell membranes.
So
Hey, how are we doing?
the little red squiggly lines going down, those are positive then, correct?
No, they have no charge.
They have no charge.
Yeah, so that would be a zero charge as opposed to the negative charge up here. Sorry, I should have drawn that. And on the next time we meet, we'll be talking about blowing this up bigger so that I don't have my jellyfish looking cartoon here. I'm going to show you what's actually in these guys. Okay. Okay, how are we doing?
Yeah.
Are you ready for me to ask you some quiz questions?
Yeah.
Because that's a good way to study. Okay, so we are, oh, whoops, I did characteristics of water next. Okay, real quick. I forgot I was going to do that next. I thought I was going to quiz you. But let's come back over here and let's talk about the characteristics of water. Okay. All right. Remember that I said that water, because they're forming these hydrogen bonds. Okay. And I'm going to do the hydrogen bonds in a little easier to see color. Okay. So I've got a hydrogen bond going here. I've got a hydrogen bond going here. So they hold together tight. Okay. We call that adhesion. Okay. So going back to my fish tank, let's say instead that this is a pond. Okay. And I've got my fish swimming around here. Okay. Now, if you've ever been to a pond, you may have seen a bug that can walk on water. Okay. You guys ever remember seeing these guys? They have their legs all splayed out and they can walk along on the water. Okay. The reason being is because of adhesion. Okay. The water molecules that are next to the air, because remember the air is mainly hydrophilic or phobic. Here, let's put some oxygen in here.
It's hydrophobic.
Very good. It's hydrophobic. So the oxygen is going to hang together, but the water is going to be attracted away from the air. And so it forms what we call surface tension. And it's enough that if you're an itty bitty bug, you can skitter around on the surface of that water. Okay. Now, the other thing is, okay, if I've got solids that have hydrophilic parts to it, okay? So let's say I've got a big old rock, okay, that is coming up out of the water, okay? The water is going to get on there and it's going to stay wet, okay? Okay. Oh, I just got the terms backwards. I'm sorry. Getting onto the rock, that's adhesion. The water holding to each other, that is cohesion. My apologies, I got my terms backwards. So cohesion is water staying together with itself. Adhesion is sticking to something that is hydrophilic but solid. Okay. Sorry, that was backwards. Now, here's what I'm getting to. You put these two together and you get capillary action. Okay, so let's say that I spill some grape juice on the counter, okay, composed of an awful lot of water, okay, and I flop a paper towel down onto it. What's going to happen? What is the grape juice going to do?
Depends
It's
on
gonna
what
go
brand
into the
it is.
napkin.
Very good. You're all correct. It's going to go into the napkin. It's going to wick in. Okay. That's capillary action. The water, okay, and the sugars and stuff that are in the grape juice, okay, are going to be attracted to the hydrophilic parts of the paper towel. Okay. And so the water is going to be attracted to it. And so it's going to move toward the paper towel, but it's going to drag everybody in the grape juice along with it. Okay. So if you're a diabetic and you don't have the fancy dancy new stuff, okay, to test your blood, traditionally you prick your finger, you stick the paper in it, and we plan on that blood wicking up into the paper. Okay. Capillary action. Okay. Also with trees, that's how water gets from the roots clear up, tends to, in case of giant sequoia, hundreds of feet high, up to the leaves. Cool, right? That is some of the characteristics of water. Okay. Now, there are other characteristics like you have to put a lot of heat into water. Okay, we'll say I've got a flame here. Okay, you got to put a lot of heat in to get it to boil. Okay, and that's why areas of the world that are close to the coast generally have a more moderate climate than we do that are landlocked and away from water. Having said that, with global warming, things are changing. The East Coast is a little less moderate than we are right now. But traditionally, the coastal areas have the nice climate, and that's why we humans like to live near the coast. Because you don't have blazingly hot summers and really, really cold winters. Okay? All right, and so there's some other characteristics of water, but the main one I want you to know is cohesion. That's water holding together. Okay. And adhesion, that's where it gets things that are hydrophilic wet. Okay, you put them together and you get capillary action. Okay. All right, are we ready for quizzes now? Have I flipped your brains inside out enough? We're not ready for a quiz. I can tell we're not ready for a quiz. Tell you what, I'm going to switch back to the PowerPoint. But go ahead, sit back, stretch, wave your arms a little bit, do a few torso twists. And give your brain a few seconds to think about something else. Okay. Deep breathing, get some oxygen to your brain as it goes through your capillaries.
Can we talk about the saltwater thing real quick?
Sorry, what?
I had a question about the saltwater thing you showed. So
Sure,
the
yeah.
saltwater would be floating around in the water.
Mhm.
So if we threw sugar in there, would it float to the bottom then?
Good question. Tell you what, let's go back to the PowerPoint. That is an excellent question.
It would dissolve too, wouldn't it?
It would dissolve. Yes, if you toss sugar in there, it's going to dissolve. Okay. And here's why. So next time we meet, we're going to talk about sugars in more detail. But let's go ahead and get some sucrose up here. Okay. So at each of these points, I have a carbon, but I'm not going to draw them. Okay. But here's an oxygen. The carbons have flipped around to form a ring. And I've got another oxygen here. And we've got another sugar. Okay. Boy, my sugars are just looking pretty sad this week. Okay, now hanging off, I got what are called hydroxyl groups. They're like I took a water, took a hydrogen off and slapped it on. Okay. So, and I'm going to leave this bond out. So when I write OH, just know that there's a covalent bond there. And I'm going to put another one here. And I've got another OH here and one here, one here, and I've got one here. Okay. So these are polar covalent bonds. Okay. So are these going to be able to hydrogen bond with water?
Yeah.
Yeah. They're going to be able to join the square dance. Okay. And that's why sugar dissolves in water. So sugar would be hydrophilic or phobic.
Would be philic.
Very good. Yes. Sugar is hydrophilic. Okay. And we'll go over this next time we meet. But here's a preview because repetition is the key to learning. Anytime you see OH or NH, it's going to be hydrophilic. Okay. If you see a lot of carbons with hydrogens, okay, without oxygens, it's going to be hydrophobic. Okay. Because carbon is smaller than oxygen or nitrogen. When it gets together with hydrogen, it shares the electrons equally. Okay. Okay, so did that answer your question?
Yeah, somewhat. But does the sugar float around in the water like the salt? That's what I was.
Oh, yes, it does float around like
Okay.
the
Oh.
salt. Yeah.
I was just wondering what the difference was. Yeah, that answers my question.
Yeah, actually, the only difference is how big the molecules are and what it tastes like. We have taste receptors on our tongue that are built to taste either sweet or salt, okay? Because our bodies need both. So it's important for us to be able to taste that delicious salty goodness or that delicious sweet goodness. And we like it even better when you put it together and make it salty sweet. But interestingly, have you ever put something into your mouth and you didn't taste it until it started to break down? Yeah, you can only taste stuff that's dissolved. It either has to be dissolved or wet. Yeah, try it next time. Take a potato chip, kind of suck the saliva out of your mouth. Gently put it on your tongue and see how long it takes for you to taste that potato chip. It's when it gets wet. Cool, right? Yeah, has to be in solution. Oh, that's one other thing with the characteristics of water I forgot to mention. It dissolves anything that's polar, that's hydrophilic. So we call it the universal solvent. Okay, so it can dissolve quite a few things. We use water to dissolve a lot of stuff. That's why we use water for cleaning, because it'll dissolve a lot of stuff. Gets rid of it, you wash it down the sink. Okay, other questions? All right, let's do some quizzes. Okay, so just as a reminder, as I bring up the question and I open up the poll, remember the polls are anonymous and this is practice, okay? Basically what we're doing is we're studying the material. So if you don't remember it right off, that is perfectly normal, okay? But as you struggle to remember, as you struggle to answer the question, your brain's going to say, hey, that's important. Okay, I've been struggling to remember that. I'm going to keep it for longer when I get the answer. Okay, so it is perfectly okay if you don't know the answer and if you get it wrong. Okay, all right, so here is my situation. Okay, let's say I'm making an Italian style dressing and I add oil, vinegar, and herbs to a container and I shake it up good. Okay, oil rises to the surface because it is A, amphipathic, B, hydrophilic, C, hydrophobic. Okay, we've got some good early voting. Okay, we're at 63%, 68. Do I hear 73, 73, 78? Let's see if we can break 90. We're stalled at 84. Okay, I think 3 of you are shy. Come on, vote. There we go. Now I just need 2 more. Okay, we're stalled at 89. There we go. Now we've got 94. Just one more and I got 100%. Hey, 94 going once, 94 going twice. Okay, I'll close the poll. Okay, most of you picked hydrophobic. Okay, we've had a few picking hydrophilic and a few picking amphipathic. Okay, all right. By the way, hydrophobic is the correct answer. Who would like to tell me why hydrophobic is the correct answer?
Because the oil moves away from the water, so it's scared, it's phobic.
Very good. It's scared, it's phobic, it moves away from the water, it does not stay dissolved. Okay. What about vinegar? Is it hydrophilic or hydrophobic or amphipathic? This one's a hard one because you probably don't know what vinegar is.
I would say that it's hydrophilic because it mixes in, or it seems to mix in pretty well with water.
It does. When you add vinegar to water, it mixes in nicely. And in fact, unless you're using distilled vinegar, okay, actually distilled vinegar is 3% acetic acid and 97% water, okay? And it's an even lower concentration if you're talking the good tasting vinegars like apple cider vinegar, red wine vinegar, okay, rice wine vinegar. Those have an even lower percentage of the acid, but it dissolves well and it doesn't separate out, okay? And the herbs are big old chunks. But what we hope to do is extract the delicious oils from the herbs into the oil part, and then the delicious hydrophilic parts end up in the vinegar part. Okay. All right, so I have a follow-up question. Hey, what type of bond or bonds does the oil have that explains its behavior? Okay. So I'm going to relaunch the poll. Okay. So is it forming hydrogen bonds? Okay. Does it have non-polar covalent? Does it have polar covalent? Okay, we've got some good early voting. Okay, we're at 78%. I need 4 more people. Okay, we're at 84%. I need 3 more people. There we go. Almost. Need 3 more people. Okay, for the sake of time, I'm going to, oh, I got another one. We're at 87. Good job. 100%. Woohoo. Okay, so we are almost evenly divided between non-polar covalent and polar covalent, okay? Which at this point is okay because it's easy to get them backwards, okay? So the correct answer is the oil has non-polar covalent bonds, okay? And like I said, at this point, it's really easy to get polar and non-polar covalent backwards, because they're pretty much the same term with just a non slapped on there, okay? But remember, the non-polar covalent bonds are equal sharing, so there's no charge. Because there's no charge, the oil can't hydrogen bond with the water, okay? It can't dissolve. All right, just for the sake of time, because we've got about 15 minutes left, we're going to zip through the next one, but next time we meet, let me know if I've got the PowerPoint available. Let me know if you want to know what the right answers are, but I'm going to let you stew about it. Okay. Okay, whoops, let's back it up. Okay, let's go to chemical reactions. And we're going to clear this. Okay. All right. So chemical reactions are where atoms or molecules are more than one atom joined together like water is. Okay, so it is when they get together or break apart. We call those chemical reactions. Okay, so let's go ahead and do the one that I started with, okay, which is where I take oxygen plus hydrogen, okay, and I add some heat, okay, energy in the form of a flame or in the atmosphere, an electrical strike, okay, and I'm going to form water, okay. That is a synthesis reaction. Okay, I'm putting things together, I'm synthesizing them. Okay, now if I were to run this the other direction, okay, so I take water and I apply some sort of energy. We'll say electrical. Okay, I run an arc through there. Okay, I can break that down back into individual oxygen and individual hydrogen, and they're going to very quickly get together. Okay, We call that decomposition. Okay. Now, this would not, going from, from water to oxygen is not going to happen all by itself. Generally, decomposition reactions tend to happen on their own with very little energy input. Okay. But it's nice to show it going the other direction when I showed you the synthesis one way and the decomposition the other way. But this is still breaking them apart. Okay. All right, let's do something a little more complicated. Okay, let's say I've got an amino acid. Through nutrition, you guys have probably heard of amino acids. Amino acids make up what? Starts with a P.
Protein.
Protein.
Protein, very good. So if you're into bodybuilding, you probably take amino acid supplements. Okay, this is the simplest amino acid. Okay, so I've got these 2 amino acids. Okay, and instead of using heat, because this process is going to happen in cells, and there's only so much heat you want to apply to a cell before you cook it. Okay, we're going to use, instead of either electricity or heat, we're going to use something called an enzyme. We're going to learn more about enzymes later, but enzymes are protein tools. Okay, they're tools made out of proteins. Okay, and in this case, the enzyme that's going to do what I want is going to act like a pair of pliers that crimps these 2 together. Okay, and what it's going to do is it's going to take this OH off, and it's going to take this hydrogen off and do the equivalent of forming water. Okay, and so I'm now going to have these 2 amino acids hooked together, okay, to make a dipeptide. So I've taken 2 smaller molecules and put them together. Sorry, I haven't given myself much room to write. And this is a special kind of synthesis reaction. Okay. And so we call this, it's a special kind of synthesis reaction that we call a dehydration reaction. Okay, because I'm removing water. If I dehydrate something, I'm taking water out of it. So if I dehydrate a grape to make a raisin, I'm sucking the water out of it. Okay, certain amount. You don't want them crispy, you still want them chewy. Okay, so that is a dehydration reaction. And it's also, when we get to metabolism, we're going to call this catabolism. Catabolism. So this comes from the same root as catastrophe. And so it's breaking down, or it's anabolism, excuse me. Getting my terms backwards again, my apologies. Okay, this is anabolism. Okay, so and kind of sounds like add. So I'm taking 2 smaller units and adding them together to make a bigger one. And we do it by removing the equivalent of water. Okay. Now I can take a different enzyme that, instead of being like pliers that kind of crimp the 2 together, can act like scissors and go snip, snip, snip. Okay. So we would take this dipeptide, and the enzyme is going to add in an OH here and an H here, and I'm going to break this apart through adding water. Okay, so we call that, so I'm going from here to here and I'm going in this direction. Okay, so we call that hydrolysis. Okay, hydro for water, lysis for breaking. Okay, so let me switch the colors here so it makes a little more sense. Be a little more consistent. So hydrolysis, I'm going this direction. I'm adding water in, okay? And a dehydration reaction is going this direction. I'm removing water, okay? So hydrolysis or hydrolysis, okay, is an example of catabolism. Okay, where I'm taking a bigger molecule and I'm breaking it down by adding water. Okay, so I'm using water to break it. Okay, how are we doing? Okay. So this is water breaking. Okay, and dehydration is a type of synthesis. Okay. Get this over here. So this is a type of synthesis. Okay. This is a type of decomposition. Okay, you doing all right? Okay, I went through that last part kind of quick. But I did want to do at least one quiz. Because like I said, it is a lovely way to study. Okay, so here is a chemical reaction that fewer and fewer of you are familiar with because we're using hydrogen peroxide on cuts less. Apparently, it causes more scarring when you clean out a cut with hydrogen peroxide. Back when I was a kid, hydrogen peroxide all the time. We also use mercurochrome. The mercura part was for mercury. I'm fine. We don't use mercurochrome very often anymore either. Okay, but hydrogen peroxide, it's H2O2. Okay, so it's kind of like water. But when it comes in contact with the enzyme catalase, okay, your tissues have catalase. Quite a few bacteria have catalase. And so if I've got a scraped knee and I put hydrogen peroxide on it, it's gonna bubble because the catalase is gonna break down the H2O2 into O2 and water, okay? And that's why it bubbles so satisfyingly. It stings, but it also bubbles and it's fun. So if you want to try this at home, if you happen to have hydrogen peroxide around, you can take your saliva and put it in a dish and then put a little bit of hydrogen peroxide and it'll bubble. It's kind of a fun experiment to do. Okay, so what kind of reaction is this? So I'm going to switch this. I'm going to stop sharing. And I'm going to switch this to a 5 answer poll. Okay, so I'm going to get so that you can see this a little better. Is it a decomposition reaction, synthesis, exchange, which we didn't talk about, dehydration, hydrolysis? Oh, we're almost to 50%. Almost. There we go. Now we broke 50%. This one is a little harder, huh? Because I went through it faster. Okay, we're at 68%.
So I'm trying to submit my answer and it won't let me.
Oh, it won't let you.
Yeah, no, it just keeps saying that there was like an error.
Oh, that's lovely. That is probably why we haven't gone up, because you haven't been able to submit an answer. I'm not sure why. I haven't ended the poll. Yeah, this is the times when it's like, yeah, I don't have a degree in IT. I'm sorry. I know microbiology. I know chemistry. All right, just for the sake of time, we're going to end poll. Okay. Most of you picked decomposition. Okay. Which is the correct answer. If you picked one of the others, that's just fine. Remember, this is practice. Okay. So who wants to tell me why it's a decomposition reaction and not, say, a hydrolysis?
Because in hydrolysis, don't you add water?
Yes, hydrolysis, you're adding water. Okay, so why is it not dehydration? I got water here.
It's still there, though.
Yeah, it is still there. Yes. And with dehydration reactions, we use that term when we're taking relatively big building blocks and snapping them together to make, like Legos. Okay. Whereas this hydrogen peroxide is degrading or decomposing into oxygen and water. Okay. And no, the reaction is not balanced. If you've taken chemistry, it's like, hey, she didn't balance her equation. Yeah, I'm too lazy to do that. Okay, any questions?
So you had you wrote down that if we put electricity to the water, the molecules will separate, right?
Yeah.
The oxygen in the water. So if we did that to salt water, what would happen to the salt?
Oh, good question. The electricity will go through salt water better because the electrons can jump from the water to the sodium, to the water, to the chlorine. I think if you put enough through, you might get oxygen and hydrogen. You might, but what's going to happen first is you're going to electrocute your fish. That'll happen before the oxygen and the hydrogen separate. And that's why electric eels are so effective. They zap their prey. They're resistant to their own shocks. Kind of cool, huh? All right. I think I had another question that I don't have time for, but take a look at this, dither over it. And next time we meet, I'll let you know what the right answer is. Okay. Okay, here's what I want you to do for next time. Okay. So we covered the first sections of chapter 2. Okay. Next time we meet, we're going to cover the biologically important macromolecules. Okay. It's about the last third of the chapter. Okay. Write down any questions you have, including what's the right answer to the questions we didn't get to. Okay. And then what we were doing with the quizzing, that's what I call active study. That's where you're forcing yourself to remember. And even if you can't remember, it's kind of like if you're trying to lift weights and you can't quite get all the way up, you're still getting some good exercise by trying. Okay. So make your brain sweat. Okay. And then, so study atoms to macromolecules, chemical bonds, and chemical reactions that make and break chemical bonds. Okay, that's what I call chemical reactions. But the section in the textbook is this big long thing. Okay. All right. Any questions?
The first case study is due at the end of this week, right?
Oh, actually, it's due not this Friday, but a week from Friday.
Oh,
Yeah,
I
the
thought
first
I
case-
thought it was
yeah.
under the February 5th, I think is when this week ends. I thought that's what it was under.
No, so the library badges do that. But I'll go back and I'll make sure that I have the correct due date. It should be February 11th. Let me pull up my calendar real quick to see. So yeah, the 4th is when the library badge is due, and then case study 1 is due on, okay, I said February 11th is when the library was due. The library badge is due on February 4th. The first case study is due on February 11th.
Okay, thank you. All right, because I think it was under the week that ended in this week, actually, February
Yes, I
5th.
have it. Oh, sorry, I'm talking over the top of you, which does not work.
No, you're fine.
So I did put it in this week's folder so that you could start on it this week. You'll also
Okay,
see
thank you.
it. Yeah, you'll see it next week too.
And we're also supposed to start working on our the biology and chemistry badge, correct?
Yeah, the biochem, the STEM one.
Yep.
Yeah.
And that one will take you more than 1 week to do. There's something like 10 different modules. So I'm giving you 3 weeks. So I'm suggesting you do about 2, maybe 3 per week. Make it much more manageable. And also the first modules will cover what we covered today.
Yeah, I went through a couple of them already. It stressed me out because it has like a 5-minute time limit on 4 questions, but eventually you get it.
Yeah, after you do it enough times, huh, Ally?
Yeah, pretty much whole afternoon.
Yeah,
it were
it says
me.
30 minutes, but that's a lie.
Yeah, I think that's a minimum suggestion.
That is a minimum suggestion. And if it were me, I would give you more time on those quizzes. But I didn't set that badge up, but it's good. Even though it's stressful, it's a good way to study. And you can take those quizzes as many times as you want. Yeah. Okay.
Wait, where do we
other-
find the area for the biology badge thing we're talking about?
Oh, yes. Want me to show you where it is?
That would be
Let me-
wonderful.
Yeah, let me go back to Blackboard. I'm gonna get out of my PowerPoint here. And let me do a screen share. Okay, so in Blackboard, when you first go in, you're gonna see this screen that has my courses and my announcements. If you scroll down to my organizations, you should see my comments. If you don't see my comments, okay, they have to add you in by hand. And so, yeah, mistakes happen. Put in a help desk ticket and say, hey, I need to be added to my comments. Okay. That's also another reason to start on that early. So you click on my comments and you're going to see a whole bunch of badges. Okay. Well, we call these badges. They're basically training, that it's kind of like the Boy Scouts, that if you do the training and you get the skills, we give you a neat badge that you can put on your Bolander. Except for it's a virtual Bolander. So over here under academic skills and support, here's the library badge. Here's the STEM biology chemistry module. Okay. And once you finish those, you come up to my badge book and you click on that and your badges will show up. Now you can see that I have not completed my library badge. But if you come down here, you can see, yes, I have completed the Blackboard badge and the OneDrive badge because I was playing around with them because they're new. When they updated Blackboard, they did not carry over my library badges. I'm offended.
So if we've already taken the library badge, do we have to take it again for your class?
No, if you've done it within the last year, you don't have to do it again. If
Okay.
it's been more than a year, I would prefer that you do it because they've got some good new stuff.
If I'm already utilizing the library to do study work, do I still have to do it?
Yeah, just go ahead and submit the badge you've already got.
Thank you.
Yeah, quite welcome. Okay, other questions? All right, I'm going